Hello world, you're listening to The Dicto. Here, I'm your host, Armin Stepanyan, and in this podcast, I'll have conversations with researchers who explore various aspects of human and machine intelligence. Through these conversations, I'll try to understand how can we implement machine intelligence in machines and dissect various aspects of human intelligence that we might take for granted. In the first episode of the podcast, a professor of cognitive robotics at the University of Manchester, Angelo Cangelosi, is joining me here today. Thank you, Angelo.
Armin. Hi.
Hi. So, could you please introduce to listeners who might not be familiar with the field, what is cognitive robotics?
Cognitive robotics is the area where we try to model the design and programming of intelligence in robots, in machines in general. It could be a humanoid robot. It could also be a car, if you think, as a robot. What's special about cognitive robotics is that you copy human intelligence, including animal intelligence, and then trying to derive an algorithm, a computer program that implements this in a robot.
So let's unpack what you just said, because there's quite a lot in there. So what exactly do you mean by modeling human or animal intelligence? Because that includes a lot of unknowns.
So the word intelligent itself is a complex concept. So for intelligence in robots and people, we mean capability to just do practical behaviors. So there is in science, in AI, there is a paper titled Elephants Don't Play Chess. This is by Rodney Brooks from MIT, one of the founders of robotics. And he said, rather than modeling high-level cognitive skills like playing chess, which most people don't really do well, why don't we focus on very simple capabilities? So one of the primary concepts of intelligence in robots and in people is the capability to survive, to find food, to see food, to discern visually where the food is from other sources. So we try to build these capabilities in robots. And then, of course, intelligence is not just behaving adaptively, but it's also doing clever things, using tools, and then using mathematics and playing chess at some point.
So right now you're mentioning kind of a spectrum of intelligence or spectrum of behaviors that we would like to model. So how does that fit into the larger idea of AI? Because there are researchers who are working on doing problem proofs, and there are other researchers who are doing very basic, as you would say, detection of food. Maybe that would be item recognition or visual entity recognition in images.
Practically, most of current applications or medium-term possible applications specialize on specific skills. So you could have a camera with an embedded intelligent algorithm in a robot or in a car or in a house that does object detection. So these are specialized systems. There are systems that do speech perception, understanding, recognition, or speech productions. Our vision is, but this is a long-term vision, is that we would like one system, a robot, a human-like robot or an animal-like robot, which combines all these skills together. So I understand language, I understand the speech, I understand the meaning. I use language to plan my food gathering tasks or my social events or my planning a mission to the moon.
All right. So how does, for example, natural language processing or computer vision that you would apply to robots differ from the standard computer vision tasks like ImageNet, for example?
I mean, computer vision is relatively similar or related in the sense that if robot needs to see obstacles in my room or objects in my room, I can use standard computer vision system to do the object detection. Of course, what's special about robot is that you coordinate your motor response to your vision. And also vision in people, that's why we look at cognitive robotics, is not passive vision. I don't fix my head and scan the objects like we do in normal computer vision. I actually move my head, my eyes to movements called saccades to actively explore the environment. So one difference between standard vision, computer vision, and robotics is that there is an active element and there is a need to coordinate your active behavior with your perceptual less, let's say, a bit passive behavior. That's one element. If you look at speech, I can have an Alexa system, digital assistant.
So just to understand, so the active element is kind of what humans naturally do that we explore around, and that's completely not captured in the standard computer vision tasks.
That's correct. Computer vision, typically Google image search, you give a static image, the system matches the similarity with some algorithms. A robot, which wants to recognize an object, will explore the object. Our eyes automatically scan the image to find features which are common. So if I show a face, experiments have shown that we look for the eyes, we look for the mouth, that's some of the components. We don't treat every individual pixel as equivalent. In computer vision, a pixel in the mouth region, in the eye region, is just a pixel. It's a gray or RGB color scale value. In a vision of a robotic active robot looking for objects, wanting to be sure that I have a bottle in front of me, the direction of the bottle orientation is specifically set for my hands to match the grasping action. There is a really continuous active movement, and there is a coordination. The next action which I produce to explore the object features are the result of my previous action, the result of the input and my scanning of the features.
Right. So how exactly do you accomplish that? What is it a rule-based mechanism, or would you have a neural net that you would train on that?
I would say that in principle, cognitive robotics, let's call it intelligent robotics. In principle, intelligent robotics is agnostic to the method. So you can use any algorithm in computer vision that used to be random forest, many other methods. In cognitive robotics, you try to constrain or justify the choice of your algorithm to the cognitive plausibility. In the sense, if I'm studying vision, and I think that we see first visual features, which are, for example, orientations on lines, which is what our brain does. So if I want to model this level of fidelity of the cognitive systems, then I would choose an algorithm that selects this type of features. So deep learning, just to be current in the approach, actually does this. The systems detect and process these early features, which are same to our early neurons in the visual cortex. So there is in cognitive robotics, which is more bio-inspired, you try to tend to choose an algorithm that matches your expectation, your strategies. In intelligent robotics, which is the wider field, it doesn't really matter. Of course, there are some of this is related to what you want to do from a epistemological, philosophical almost point of view. Sometimes technically, you might have to sacrifice your inspiration to biology and human cognition to find shortcuts and use, a reasoning system if this is what suits you.
Right. So what you touched on another kind of topic I would like to explore a little bit more. How do you connect the biological concepts, the psychological concepts to robotics, and then bring them back to bring the models that you find, the findings from those models back to the original biology? How do you justify it?
So in cognitive robotics, before we start looking at the robots, we look at human cognition, which is really psychology or neuroscience studies. In psychology and neuroscience, there are theories based on data that say that, for example, when we scan a photo, when we look at a photo of a face, we look for specific features to verify, our expected presence of two eyes, a nose, and a mouth. So we start from these theories. Sometimes we start even from data, and then we try to match algorithms that allow us to verify this. As I mentioned before, if we know that in vision, the brain goes hierarchically through a series of features of increased complexity. So at the beginning, the first cells in the area called V1, the back of the brain is a visual area with cells called layer V1, vision 1. We only see lines which are have different orientations, and we also see lines of different thickness. This is what the cells. If you cut my brain and you only leave the V1 cells, this is what I experience. Lines and contrast and this type of basic elements. But then at the next layer called V2, you can combine a vertical line and horizontal line and you form a corner. That's a more complex feature.
I can see the parallel to convolutional neural nets where with additional hierarchy they learn more complex feature identification. However, the way I would look at it is that we made a set of experiments, found out that convolutional neural nets perform well, asked ourselves why do they perform well, and figured out that that is because they make this hierarchical distinction. And then now, based on this knowledge that we have about the method, and based on the knowledge that we have about the human brain, we connect the two together.
That's correct. But also in the design of convolutional neural networks, the idea that you have a filter that convolutes, scans the image, is the same filter. This is actually in the design of the system itself based on knowledge of our vision system. So we know that our vision system is scanning for basic features and then more complex features. Of course.
So would this can be the kernel application on the kernel?
Yeah, it would be the convolution of your kernel filter over the image, which is what different neurons would be doing on the input from the retina, and of course a bit more complex processing between the retina and the actual visual area called V1. So some is in the design. Of course, then we need to check that our original design corresponds to functionally the selection of these features. So like you were saying, we know this is the case, and therefore if I want to do cognitive vision, one of the obvious starting point would be to use this. In computer visions, there used to be an approach called SIFT, S-I-F-T, which were a series of, not random, but any possible feature that I can extract from from a set of pixels was a starting point to then try to look for similarities or correlations. Here, the features are brain-inspired in some way because we use a convolution, we use filters, we use pooling, and they correspond to these different types of cells in the visual cortex.
So how do you go from identifying a single method, so in this case, the convolutional neural network, to building an entire system? I'm thinking something like the baby robot that you built, the iCub.
So the idea is that you don't have in a convolution network, there is a fixed number of layers, and they only specialize for a specific task, let's say vision to classification. There are, again, other areas in the brain called AIT, in the visual cortex, which start to identify and respond, neurons that respond when you see a specific type of object, which could be considered, let's say, the output units, these response units that you get in a convolutional neural network. Of course, our category recognition is then linked to speech recognition of specific sounds like cat, dog, if I see a picture of a cat or a dog. So in a global vision of a baby brain, we want a system which has different neural networks which talk to each other, hierarchically organized. And of course, in a baby brain, which is the area that we call developmental robotics, we would like to model how a grown-up robot doing complex stuff actually reaches the stages, first by building incremental knowledge of simple object recognition, or in language, simple sound recognition. That's what we do when we do babbling as babies. So we first experiment as babies to the sound system in our own language. We receive input from our culture. We respond, we train our speech and articulation system and sound recognition. Then we start to combine these sounds into words. Then we combine two words together, first isolated words, milk, bread, want, and then you can say want milk. Then you can add more complex knowledge of syntax. I want milk, you eat, she eats. We start to distinguish all these rules. This is incremental developmental intelligence. Within cognitive robotics, we have this approach called developmental robotics that models baby brains, the growth of baby brains and baby bodies, of course.
So then the connection is still not quite clear to me. Then how do you make that leap from just being able to identify images to having understanding of intent, setting goals, and movement in space? How do you go for that whole package of the baby?
These are hard challenges. So we are modeling some.
But the reason why I'm asking that is because you solved a significant step of it. As far as I understand, some of the work that you did on the iCub has been integrated back into applying it for psychology experiments.
Yes, and we've done work on intention recognition, for example. How do you recognize what the person or the robot wants to do next, so that in a collaborative task you help? How do you make this link? Building a model, a computer model or a theoretical model of human behavior, it's a simplification. And the reason we build models in science is you build, you think it's right, and you want to prove if it's actually right or wrong, a theory, an hypothesis, or a model. So you design a new experiment in psychology or in robotics that tries to prove or disprove your theory. So my theory says when I look at the face, I look at the eyes and then at the mouth, but I ignore the nose. Let's say this is not important. This is my model. Then I design an experiment where I manipulate faces with or without noses, or with the nose in different parts. If my data prove the point that the noses don't matter wherever they are, then I'm adjusting my model. So this shows how you start from a psychology data, scanning of faces, create a model. Eyes, mouths are important, nose not. This is just a hypothetical model. You go back to your data and you verify this. What we do in robotics is that in addition to having a theoretical model, we implement this model into a computer program. We give it to a robot. We make the robot scan faces, let's say in this context. If the robot's behavior is similar to the person's behavior, to people behavior, then we can say that the model is valid. Of course, it's an incremental validation. There is no super model. There are very few super models, let's say in physics, Einstein's principle, but even there, relativity changed the way we see things. So in the human context, maybe we will go through the same stages.
Right, that's curious. Then thanks for explaining how you validate whether your model of your robot model of the psychological theory is correct. And how do you go the other way? Using the robot, how do you give back to the psychological theory?
So we have an example that some work we did in our lab. First, we noticed from psychology papers that children learn to understand the first words not by sitting passively being taught with images, the name of objects, but through an active engagement of the child with the object. So the child touches the object, rotates the object while the object is being named by the teacher, by the parent or the peer or a teacher. This is what we learned about by reading psychology papers. And we built a model of this behavior with a robot that was actively exploring these objects being named. In addition, in psychology, they demonstrated that if I play with an object as a child, and then you teacher hide the object for a second, but you keep my attention in the same space, I can actually learn the name of the object even if the object is named when the object is taken away. This is starting from psychology. So we built a model where the robot moves around. At some point, the robot stops seeing the object which is hidden. The person names the object, and we demonstrated the object can learn like a child to name the object when it's visible and when it's not visible. What we did in addition in our experiment, this is how we went from robot to behavior. By chance almost, we started to extend the direction of movement being controlled in a robotic experiment from left to right, which is what they did with children. You hide the object or move the object left to right only. We started to manipulate.
So what do you mean here? Could you describe a little bit more the setting of the experiment?
In the experiment, the child sees two objects, and the two objects are novel. The child doesn't know the name. These are almost 2-year-old babies. They can learn words if you repeat the name a few times. In some cases, once is enough, but sometimes you need to repeat it. So you show the two objects on the left, on the right of the table. The child moves her body to play with the two objects. Then you hide one object. You hide the object they are playing with on the left. And while the child is still playing in the left area of the table, you say, this is a bottle. So for the first time, you hear the word bottle, but you don't see the bottle, but you were playing with the bottle before on the left part. That's what they do in psychology. Of course, in psychology, they run many experiments. First, the bottle is on the left, then it's on the right. So you move the object to make sure that you are really understanding. The children use a strategy of, we say, postural attention. The body orientation towards the left and the right is your cue to where the important object will appear or will be named. So we built a model where our iCub robot, this baby robot, moves left and right with its body to play with two objects on the left and the right, and then the experimenter in some conditions hides the object on the left and he says this is the bottle, and you will show later that the object is recognized by the robot. This was our psychology experiments. We did the studies in the robot behaved like a child. What we then started to do is to move the objects up and down. So in addition to left and right, up and down. And we noticed that children use this extra dimension of movement as a way to learn more words. So our robot was able to learn more objects, the names of more objects, by playing both the left and right and the vertical and bottom, top and bottom dimension. This was a prediction. We observed this in our robot, but we didn't know if this was really true in children. So our collaborators in Indiana, in the US, Bloomington, where Indiana University is, they run new experiments replicating, in this case, our robot data. So we replicated their data of after the experiment. We extended the experiment, and they demonstrated it is true. Now we know that children use vertical movements in addition to horizontal movements to learn more words. So that's the way we link the two.
That sounds amazing. I think it's so interesting how essentially a bug in your initial code resulted in a large feature for the research.
Really the researcher playing with a robot and trying something new. It wasn't really intentional.